doing today?
Good.
Better now that I've eaten. I'm still sleepy though. Never feels like I have enough time for lunch break. Alright, so we are back to at least run a meeting schedule, normal type meetings for fall of 2020 at least. If you as an individual are still unable to make normal in-person lectures, that is fine. The recordings exist, the pre-recorded lectures exist. I'll be sending out informational emails if this. I already need to drink water. I'm glad to see you all. And I hope that you have been staying healthy and making good choices to continue to stay healthy. Some announcements before we continue today. The Chapter 7 assignments are due tonight, and regarding those, I'll open up the floor for everyone to be able to ask any questions about any of the Chapter 7 assignments that you have. One specific thing that did come up: we have not finished the lab yet. You may have noticed this, what's currently on screen, will be on screen, is the Chapter 7 lab, which is due today. And this one requires the use of 2 different simulations. Now, unfortunately, and I apologize, the link that I put here in the original was wrong. It was a link from a previous lab because I tend to edit the same document to keep all the formatting intact. So the lab that was there was, like, the link to the second lab was wrong. This is the correct link, and that new link is on the version that is on the Brightspace page. So if you have not done the lab and you have not encountered that issue and then found the correct simulator on the website, that is the correct link. It should be the States of Matter Basics lab, the simulator, and this is what it should look like when you get it up and running. So, if you haven't finished yet, go to the updated copy for the updated correct link. The Chapter 7 stuff is due tonight. We're going to begin Chapter 8 today, which is a direct continuation of Chapter 7. Still more information about heat and thermal energy. And currently the Chapter 8 assignments are due next Tuesday. The homework and quiz are already live. We're going to have a lab this week. And it is available for students to come into the room to take an in-person lab. As you can see, we have very stylish styrofoam cups and thermometers scattered around the room for use in a heat transfer specific heat lab. So we will have normal lab meetings this week. But to look to the future and to next week, we will, as we wrap up Chapter 8 this week, we're going to transition next week into Test 2 territory. Our 2 tests have been on Chapters 1 through 4, the first core, and then Chapters 5 through 8, the second core. So once we finish Chapter 8 this week, we'll move into that second test-taking mode next week. The way the test works will be the same. We'll spend the beginning of next week reviewing, and then the test will be made available to you to take at any point between the end of next week into the Monday of the week after. Same rules, same, find a nice quiet space where you feel comfortable working for as long as you'll need, and I'll send you the test when you're ready. Because there will be a test starting next week. You don't have to take it as soon as it's available, but because a test will soon be available to you, there won't be any lab at all next week. So, normal lab this week, no lab next week. So that you have time to study, but also next Tuesday is also election day, and I know everyone's going to have a slightly different voting situation, just depending on where your home address is. But just to make absolutely certain that people have as much time as they need to vote, because voting is important, we won't have any in-person meetings at all next Tuesday. I'm giving you guys the day off from coming here so you can vote. Voting's important. Even if you already voted like through the mail or whatever your specific situation is, I still think election day should be a holiday anyway. So in that spirit, there we go. Now, because we're reviewing for tests next week, I will still be posting video content to help with that. I'll have video calls that you can tune into when you're available and not voting. For any questions, I'll post practice questions. I'll make sure everyone knows what content is on the test. We will have plenty of opportunities to converse and talk about the test and study. So even if we're not meeting in person on Tuesday, I will still be available to you. So I guess just to recap the schedule for the next couple of weeks, this week is Chapter 8, a normal week with a normal lab and normal homework and quiz. Next week is a review for the test, which will be there we go. So this week, Chapter 8. Next week, November 3rd is Election Day. No in-person meetings that day. Instead, I will offer remote meet calls that you can attend for review. But this will be test review week. We will review remotely together this day. Test will open up for you to be able to start taking it around Wednesday to Thursday, and will continue through to next Monday. Thursday, we'll meet, have normal classes if you want to come in to attend those for review. We'll go through practice questions, go through everything on the test. Same with Friday. No lab at all next week. Then the week after that, we're going into November now. So first week in November is test week. No in-person meetings, in-person review meetings every other time. The week after that, for the next couple of weeks after that point, we're going to focus on some additional topics that you should know to exist on planet Earth. But any additional information that we cover this week will simply be added onto the final exam. There's no test for it. This week, we will be wrapping up those additional topics and doing exam review. And then this is exam days, and then you go home for Thanksgiving, and you get to have a nice long break. That's the rest of the semester. We're in the last stretch. Any questions about any scheduling issues related to the class before I go with the Florida Chapter 7 questions? Okay. I will also be sending this information out in an email because some people, I know I like having it written down in a place that I can't lose, so I'll give you the same courtesy. All right. If you have any comments or concerns at any time, please let me know. Now, the Chapter 7 assignments are due tonight, so do you have any questions about those before we move on to Chapter 8? Any questions at all? Even if you don't, there's a couple of things I'd like to go ahead and common questions I've gotten from these assignments that I'd like to show and talk about with you guys. Okay. So, what's currently on screen now is the Chapter 7 homework. Chapter 7 homework. This is problem 5. Let's talk about these in order. Okay. So, there's a couple of homework questions that I've gotten repeatedly, so just to address them with the group while you're here. Number 5, a lot of these questions are going to involve the specific heat formula. That is Q equals mc delta T. And this problem is no different. We're going to be looking at the temperature increase in a sample of water. So we want the heat added to the water is equal to the mass of the water times the specific heat of water, which is a constant 4,186 joules per kilogram times degree Celsius times delta T. Note that the question is asking you for delta T. You want to solve for all of delta T equals blank. Now, we know mass of water, we know specific heat of water, we want delta T. We need to figure out how much energy is added to the water as it falls off of the, what's it called? Salto and Gel in International Park, Venezuela. Now, any form of energy can convert into thermal energy. Every time anything happens, some amount of energy involved in the process becomes thermal energy. The process here is water falls off of a waterfall. Before it fell, what type of energy did it have? What type of potential? Very good. So it had GPE, the formula for which is mgh. So we can figure out how much energy it had before it fell off. We know its mass, we know 9.8, we know how high up it was. And the question tells us that there's a certain percentage of that energy which becomes thermal energy. So what you're going to do is, we're going to plug in for Q is mgh times your percentage. If 13% of this becomes thermal energy, you need to multiply this by 13%, which is 0.13. Any questions about that one? Okay. I'm also going to ask about number 6. Now this one is also a Q equals mc delta T question, except the object we're looking at here is a person. But same basic formula, a certain amount of energy being added to the person. She has a certain mass. We're assuming her body is entirely water. So this will be her specific heat. And we want to know how much her temperature will increase from all of this energy that she is absorbing. You do have to find that total energy again. And specifically, you're going to need to convert from kilocalories into joules. When you eat food, the packaging will tell you how many kilocalories is in that food. And just for your benefit, because I don't think I actually wrote this down before, this is the conversion between kilocalories and joules. 1 kilocalorie is 4,184 joules. You convert kilocalories eaten into joules, then you need to pay attention to how much of that energy becomes thermal energy, because not every joule you eat goes into warmth. So whatever your energy is, multiply it by 0.8, and then you can plug it in for Q. Solve for delta T to figure out how much the human's temperature would increase from this, assuming that you did not bend this heat in any way, shape, or form. Keep in mind this will be in Celsius, so remember that you'll get a Celsius number, and keep that in mind when you answer the next question. And then the last part of the question asks about what processes the human body can or won't lose heat from. We are warm-blooded creatures. We make our own heat, but sometimes we have too much and we need to get rid of it. just to help benefit you guys, because Sapling doesn't count these questions as correct unless it's completely correct. Of these 5 options for how a person might vent heat from their body, only one of them is a method that humans cannot use. One of these methods won't go in here. 4 of the 5 are correct, and 4 of the 5 need to be in here. Okay? So you need to pick the 4 of these that a human can use to vent thermal energy from their bodies. So that's 6. Also, so this is the last homework question I've been asked about repeatedly. And this one is an issue simply because it's another one of those questions that Sapling doesn't count any points for unless it's completely correct, which I dislike, so I'm giving you the hint. For this question, we are looking at, this is homework question number 9, each of the 3 methods of heat transfer: conduction, convection, and radiation. And there are 9 examples of heat transferring down here in the answer bank. You need to drag these up into the method of heat transfer that they best match to. To go ahead and help you guys, each column needs 3 answers in it. Of these 9, 3 belong in each. So each column should have 3, and they all should be used. Okay? Those are the things that I've found people having the most issue with. If you have any questions while working your homework, please let me know at absolutely any time. Please email me. I will be awake until midnight for sure. Anything else? Any other concerns or questions or issues from you guys about Chapter 7 stuff before we start talking about Chapter 8 stuff? Okay. If you have any questions, please interrupt me at any time. I'm asking you to interrupt me. Now, Chapter 8 is a direct continuation of what we've been doing. The title is Thermodynamics. If you have not heard this word before, I'm going to look at the root meanings really quickly. Thermo means of or referring to heat and temperature. Dynamics means motion. A dynamic system is a moving system. So thermodynamics is the study of the movement and transfer and interactions of thermal energy, which is what we've already been doing. We're just now going to look at, very specifically, the laws of thermodynamics. In the first 4 chapters, we were looking very extensively at Newton's 3 laws of motion, which are very foundational to our entire understanding of how matter and forces move and interact in our entire universe. These laws are as important for our understanding of energy as a whole. So they're sort of a very good counterpart. Now, traditionally, there are 3 laws of thermodynamics, the ones labeled first, second, and third. But later additions and later physicists have been adding an additional 0th law of thermodynamics. 0th is like the equivalent of first, second, or third, but for 0. So it's up there because it's sort of a conceptual understanding that you need to have before you look at the others. It's like the prologue to the novel before you get to chapter 1. It's not really a law on its own. It's just a quick, brief statement to give you insights to the other laws and something to cover before them. So there's technically 4 laws of thermodynamics. There's 1, 2, 3, and 0. And we're going to spend time talking about each one of them. But since we're already on the slide, and since you're already copying things down, let's just read each one brief and give a brief summation of it. The 0th law of thermodynamics is basically just the commutative law of temperatures. Let's say that this basketball is object A, this foam ball is object B, and I am object C. If the basketball and I are at the same temperature, then we are in thermal equilibrium. If the foam ball and I are at the same temperature, we are in thermal equilibrium. If each of these objects is at the same temperature as me, then the two balls must be at the same temperature as each other. If A equals C and B equals C, then A equals B. It's the same thing as the commutative law in mathematics, it's just applying to temperature. This is not revolutionary, so this is here because it's just a statement that is written in all the books before you get to the meat and potatoes laws. Speaking of, the first law of thermodynamics is very important and very often quoted, and we have talked about it already because it is also known as the law of conservation of energy. This is the law that states energy cannot be created or destroyed. The total energy of the entire universe is constant, but also the total energy within a specific system, a specific part of the universe, is also constant. Second law actually the second and the third law both talk about entropy, and just as a preview of entropy, like the elevator pitch for what entropy means loosely translates to chaos and disorder. The second law states that the universe tends to become more disordered as time goes on. Every process tends to create more entropy and more disorder. Third law states that you can reduce the chaos of a specific object, and you do this by decreasing its temperature down to absolute zero. You can decrease the chaos of a particular part of a system, but the second law then states that the total chaos level of the entire universe cannot drop. You can reduce it for one object. You can say make your room more organized. But the universe as a whole will stay as chaotic, if not become more so. We'll go into more detail with all of these things later. This is not the last time we'll talk about each of these laws. This is just the elevator pitch before we move on to talk about each one individually. You also have this slide. This whole slideshow is on the Brightspace page. This information still exists if you don't copy down every single word of it right now. Additionally, this is probably one of the Wikipedia pages that gets the most views, is just listing these three laws. So these are known constants to you, the information is available. Now, there's some words that have been tossed around in these definitions, in my explanations of even the last couple of chapters, that some terms that I think are important to define before we continue. When I refer to a system, I am referring to the specific objects in the equation that we are looking at. A system is whatever you are examining, and a system can be as big as the entire universe or as small as a single electron. It just depends on the question. The system is whatever portion of existence you are analyzing in that moment. And everything else is the surroundings. If you're looking at just one electron, then the rest of the entire universe is its surroundings. If you're looking at the universe as a whole, you don't know what its surroundings are, stay tuned for that. But when I refer to a system in an example, I'm referring to whatever we are analyzing in this moment. Okay? Any questions before we start looking at each law individually? All right. We're going to start with the simplest law, the one that comes first written numerically. That's zeroth. Again, this is very simple. Don't need to spend much time on it. It's just the commutative law of temperatures. As an example right here, both objects become the same temperature as the air around them, It means that they, as long as they're in the same air, then they must be the same temperature as one another. By that same logic, most of the inanimate objects in this room should also be about the same temperature. So, just communicated law of temperatures. Now, I guess you could suppose this is a formula. You could probably call it that. But now we're going to actually look at the first real formula of Chapter 8, which is the mathematical version of the first law of thermodynamics. Energy cannot be created or destroyed. There has always been my throat which dries out when I talk. Sorry about that. So, if you look at the universe as a whole, for as long as the universe has existed, as far as we know, as far as all of our material units are able to measure, there has been a constant amount of energy stored throughout the entire universe. From the beginning, from the point when all of the matter in the universe began existing, the amount of energy level that the universe had then is the same as it is now. That energy has changed states, it has changed what has possessed it, stars have exploded, planets have lived and died, but the total present of the entire bubble that is our universe, as we presently understand it, has been constant. This is also true for individual systems. As soon as you define what a system is, the amount of energy in that system is constant. Now, if you're only looking at part of the universe, it is possible for something outside the system to come in and give it more energy. Maybe this is potentially possible with our universe as a whole. If something can come in from outside the universe to give it more energy, I believe that to be possible, but at least for this class, we're assuming that the total energy level of this system is constant, which means that if energy within that system changes states or changes what object possesses it, all the numbers still have to add up correctly to make sense. The formula we're going to use to represent that is here on the screen. It says that delta U equals Q minus W. Now the U term, I realize it's labeled up here, the U term represents total internal energy that an object possesses. This is every piece of energy that that object is storing within itself in any form. This most often takes the form of thermal energy, but an object can possess other energy types too. And keep in mind, this is a delta U. This is just the change in the internal energy of an object. It's very hard to know how much energy an object possesses in its totality, because that kind of depends on your frame of reference. From our frame of reference sitting in this room, that chair isn't moving, so it doesn't possess any kinetic energy. But from the point of view of galactic center, that chair is spiraling around it at millions of miles a second. So, from some point of view, it has more energy than it does from our point of view. So we're only looking at how much its energy level changes based on what's happening to it within the system. So, an object's energy level will change based upon heat added into the object. Q is going to represent heat added to the object. If you come in from outside the object to give it thermal energy, then you would add in a positive amount of Q. And its internal energy level can also change based on the work done by the object or the work done on the object. We've talked about work before. Let's say that I take this chair, I exert a force to make it move a distance, and it starts moving. I'm doing work on the chair. It now has more energy than it did before I started. When I do work upon the chair, I am giving it energy. So we very commonly in our day-to-day lives do work on objects and give them more energy than they otherwise would have had. But it's also possible for an object to do work on something else. Now, this chair probably won't be doing much work. It doesn't have any moving parts. But we have invented machines whose entire purpose is to do tasks for us, to literally do work for us. So, an object, a system, is capable of performing work. And when you do work, you use up energy and put it somewhere else. If you consider myself to be a machine, I do work. If I do 1,000 joules worth of work, that's 1,000 joules I no longer have. So when an object performs work, or a person, a being, when any part of a system performs work, you would plug in a positive number here. I know there's already a negative, that's my design. When a system does its own work, it loses energy. So you plug a positive number in, and that results in energy being lost from the object. Meanwhile, if work is done on something, you are giving it additional extra energy that it didn't already have. So then you plug in a negative work, that negative becomes positive, and then you end up giving energy to the system. You would drive its total energy level up. I think a good example of this specific type of interaction is a piston, which is what this drawing is supposed to be. I'm not an artist. Let's see if I can actually find the number. Well, darn, all that work and we can't find the original one. Isn't that just how it goes? Okay, so a piston is a machine designed to do work because it's going to expand under specific circumstances and contract under other ones. If you've ever done anything related to cars, you've probably seen pistons firing an engine. What happens is, in most pneumatic pistons, there's usually some amount of gas inside of this tank, and various things like heating that gas up are going to cause it to expand. When the gas inside expands, it's going to press the end of the piston outwards. As this extends outwards, it's going to literally push on whatever it's up against and do work on it. So this is one of the earliest, simplest machines. You add energy into the system by heating the gas. When you heat anything, it's going to expand, especially gases. The expansion of that gas causes this to push out, push on something, and do work. You feed thermal energy in, and it does work out. So as this expands and it pushes on something else, this object is doing work. It's exerting a force and making something move. You can see this in the cylinders of an engine. You can also see it if you've ever looked at like an old-timey train. If you've ever noticed, there's usually a piston that pushes forwards and makes the wheels spin forwards, and then as it comes back in on the return stroke, it pulls the wheels back, and it keeps going back and forth to make the wheels keep going on an old steam engine. This is how all of those machines, pretty much most of our ground transportation works. So this object does work when you give it energy. And I made the notes go. What ultimately happens is, you are going to, usually if you want a machine to do work, you're going to give it thermal energy and it'll output work. Usually with a small amount of change to its own internal energy in the process. The reverse is also true. You can do work on a system and give it energy. For example, if some outside force pushes in on the piston, you will add in, you're doing work upon the piston and putting energy back into its system. As an example of this, I actually have a piston up here. And this is just a very simple plunger system that presses into a closed cylinder of air. There's just air in here. And when I press in on the cylinder, I'm just compressing the air. But to show that I am putting energy into this system when I compress it, I am going to first try to get the dust out of it. And fail to do so. And what I'm going to do is I'm going to add a very small amount of pocket lint into the tube. This is literally lint from my pocket. I'm just going to drop that in. And now there is a small amount of pocket lint at the very bottom. The reason I've placed that in there is so that when I add energy into the system, it will cause a visual change that you can see. So, right now, this is a closed system. No air is going in or out. What I'm going to do in a second is I'm going to slam down on the plunger. That's going to, I'm going to do work on the system and give it energy. And then we're going to see what happens when it has that energy. Now, I'm hoping something very specific will happen. And to help you guys see it, if it happens, I'm actually going to turn the lights on. Now, I put lint in there because lint can burn. What happens when you add energy to something that can burn? So everyone watch right around here. I'm hoping I'll do this right. There's a chance it won't work. If it doesn't work, there's something else I will show you instead. But best case scenario, you should see something pretty cool. Ah, well. There it is. Please tell me you saw it.
Yep.
Okay, what happened?
Fire.
Fire. As I did work on the system, I gave it energy. That's going to ultimately increase its own internal energy. And when you add energy to something that can combust, it tends to combust. So I created fire. Additionally though, for the less fun version, if I do this repeatedly, it's harder to see, but at least the people that are closer to the front, pay attention to what it looks like now versus now. See anything? Smoke. So I've sort of expended the big boom, but it still makes smoke when I add energy to it. And now I really clean it out. So, the entire time the piston has been in the system. If the gas inside of it expands, it does work. If something else does work on the system, it's going to push in and contract it. And that will ultimately end up affecting the total amount of energy that the system has. The terms in the previous equation listed here. Q represents the thermal energy added into the system. You're plugging a positive number if you are adding thermal energy into the device. It'll be a negative number if thermal energy is leaving the device. W is the work. You plug in a positive number if work is being done by the system. So when I press in on the cylinder, I'm doing work on the system. You plug in a negative number. And then the U is the internal energy. If the object's internal energy does not change, then delta U is 0. If delta U is a positive number, that means the object gains some amount of internal energy in the interaction, and that means its temperature should go up. And the amount of energy that is staying inside of it rose. Its particles are now moving around more, its temperature will rise. Meanwhile, if delta U is negative, its temperature will drop. To utilize these principles very quickly, these are two very quick examples that we're going to work together. So delta U equals Q minus W. The first one, we're going to add 600 joules of thermal energy into the air tank of a piston. So, if your machine has a piston in it, you want the piston to expand, you're going to do that by adding thermal energy into the gas inside of the piston. So we add 600 joules, and that gas will expand and press outwards on the plunger, pushing out and doing work. So, we're going to add 600 joules of thermal energy, and the system will do 400 joules worth of work. And so we're adding thermal energy, plugging a positive Q. Since the system is doing work, this is the work the system does, also plug in a positive number. Now what this means is, you want this machine to do a task. And it does 400 joules worth of task. But you gave it 600 joules worth of energy. You gave it 600, but it only did 400. The reason this formula ties into the first law of thermodynamics is the difference in energy here has to be somewhere. And the place where it is inside the object. Some of it just got stuck and stayed there. So, the object retained 200 joules worth of thermal energy. With 600 in, you got 400 out, so 200 stayed behind. That energy is not accomplishing anything, it's not doing work. All it's doing is making the gas warmer. Every single machine, including the human body, behaves similarly to this. If you want to do 10 joules of work, if your output is 10 joules, you're probably going to need to put in more than 10 joules worth of energy to start the process up. Every task in the universe is inefficient in that some energy always stays behind and makes the object warmer. It just stays behind as internal thermal energy. Every single thing does this. Our body does this, all machines do it. As long as there is friction and material objects are touching each other, you will never get as much out as you put in. Any questions about that one? All right. Now the second one, We're going to assume in this one that delta U remains 0 and that the process is 100% efficient, just for simplicity's sake. A second machine pushes into the piston and does 1,000 joules worth of work into the machine. Work is being done on the machine now. And we're told the total energy of the piston does not change. So for this version, delta U will be 0. Q is unknown. And we are adding 1,000 joules worth of energy into the system. When work is done on the object, you plug in a negative number, because that's not work the object is doing, it's work done on the object. But these negatives will cancel, so ultimately this will be Q plus 1,000. However, we are solving for Q. 0 equals Q minus negative 1,000. So if you were to do this, if you were to do work on a system and its internal energy level did not change, that means that every single joule of energy you put into it is going to escape it as thermal energy. If you did have a process that did not change the internal energy level of an object, it was 100% efficient, none of the energy stayed behind, any energy you put in will come back out. In this case, you do work on the piston and the energy comes out as heat. Notice the negative, this means the object is losing thermal energy. Any questions about these at all? Okay. Now, before we move on, I actually want to address something because I don't believe I mentioned it yet. Objects expand when they get warm. I mentioned that just now with the piston. There's gas in here, you heat up the gas expands, that's what causes the piston to push out. You see this in a car engine when what the engine does is it brings in gas fumes, ignites them, there's a little explosion as gases get hot and expand. An explosion is usually just a rapid expansion of gas. The gas gets hot, it expands, it presses out on a piston, and that energy gets translated into the motion of tires. Gases are the things that expand the most when they're hot, but all objects, even solids, expand when warm. Called the principle of thermal expansion. And if you've ever worn rings on your fingers, you've probably dealt with this before. Because when you put the ring on in the morning and it's just cold metal, it's at its smallest. But if you, even just being on the finger of you, a warm-blooded organism, and especially during summer, when you spend the amount of time outside, you ever notice that by the end of the day, the ring feels looser, and maybe uncomfortable? When it got warmer, it expanded. Conversely, if you put it on when it's warm and then it cools off, it will shrink around your finger. I have an uncle who, due to an unfortunate accident when he was a teenager, only has like a piece of his ring finger left. He lost about 2.5 fingers. And just because of the surgery, what's left of his ring finger is a lot wider than it should be. So in order to get his wedding ring on, he has to cool his hand down to shrink it and warm the ring up to heat it, get it on there, and then it stays there and doesn't come off. Additionally, for one thing, the, what's it called? Empire State Building is tallest on the hottest day of summer. And architects do have to account for this in all of their designs. Because different materials expand at different rates. And if part of the building expands at a greater rate than the other, it will probably fall apart. Related to that, you ever driven across a bridge where you've noticed like maybe every couple of yards these weird this weird metal break in the road? It's usually got metal interlocking teeth, and as you drive over it, you just kind of go thump, 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 thump. those are there because thankfully the civil engineers who built the bridge factored in the fact that during the heat of summer, the bridge is going to expand. Concrete that makes up bridges expands at a decent rate compared to, say, wood. And if you just laid a slab of concrete in the ground, when it heats up in summer, it's going to expand and press into the ground on either sides of the bridge. If there's no room for it to expand, it's just going to kind of buckle upwards and crack, which no one wants. So the engineers built spacers. Those metal gaps are spacers so that each piece of the bridge can expand into the teeth of the next one. So if it annoys you, I'm sorry when you go over those little ridges, but if they weren't out there, the bridge would not last a year. So, bonus lecture on thermal expansion. Be aware of it. It does affect your lives. Excuse me. Any questions before we continue? Okay. So we talked about zeroth and second. This is now we talked about zeroth and first laws. So this is the second law of thermodynamics. First law said energy can't be created or destroyed. This law says that entropy of a system will either stay the same or rise. Now, entropy can be described as chaos, as disorder. It's more scientifically referring to the movement of the subatomic particles within an object. The warmer something is, the more its particles move around. Because they're moving more, they tend to space farther apart, which is why objects expand when they're warm. And the more the particles of an object move around, the more chaotic the system is, the more entropy it has. You could say the more entropic the system is. That is a word that gets used sometimes. Now, as I said before, every single process creates some amount of thermal energy. If you want to do 10 joules of work, you probably had to put in 11 joules worth of energy. 10 of those joules didn't be wanted, but 1 joule stays behind as useless thermal energy in the parts of the mechanism, just making the machine warmer. This is one reason why machines overheat. You leave your computer on for a very long amount of time. Some of the energy it uses to operate just gets lost to thermal energy in its wires and it heats up. Don't let your computers melt. It's why the engine of your car gets hot and stays that way while you're running it. And sometimes that overheats too. Every single system creates thermal energy every single time it moves. This includes your body, which is one reason why it's easy to warm up if you are physically moving around. You make more heat that way. And the more heat something has, the more its particles move, the more chaotic it is on a molecular level and the more entropy it has. So every single action creates more thermal energy. That means the particles that make up that object move more. That means it becomes more chaotic. It has more entropy as a result. Because every single movement does this, anytime something moves, entropy in the entire universe is always rising. Every single moment, more energy becomes thermal energy contributing to entropy than there was a second ago. Total energy in the entire universe stays the same, but I presume at the beginning of Earth, there was more energy in forms other than thermal energy. There used to be a lot more energy stored in the fossil fuels and in potential energy and things like that. Now a lot more of it is thermal, making more chaos. So the chaos level of the entire universe has been rising since the creation of everything. It's theoretically possible to not make thermal energy by accident, in which case entropy level stays the same. So hypothetically, if a system was completely efficient, entropy levels remain constant. But in every real system, entropy levels will rise. And the entropy of the entire universe never goes down. If you've ever heard the term heat death of the universe, that's referring to the point where all energy is now thermal energy and there's no energy left to do anything. That's the point where we've reached matrix entropy. You can transfer entropy out of one object and into another. You can drive down the entropy level of a single object, but not the universe as a whole. And to sort of epitomize all of this into a euphemism, when you do something, odds are you cannot completely undo it. In doing the action, you've created some amount of disorder you cannot reverse. Now, we can calculate the amount of energy an object possesses, how much its entropy changes, and in general, the warmer something is, the more entropy it's going to have. And so, this is just so that we can compare how much entropy one object has compared to a different object. It's just so that you can understand the comparison. This formula says change in entropy for any object will be equal to the thermal energy it gains in the activity divided by its current temperature in Kelvin. That's important to note. You have to put Kelvin units here. Celsius won't work because at Celsius you would have zero entropy at the freezing point of water. So it has to be Kelvins. This formula will tell you what system is more chaotic than another one. That's what it's here for, just to give us sort of a comparison. And this is the change in entropy for a single object. For the entire universe, every single action, entropy will either stay at the same level or it will rise for the entire universe as a whole. So this is the second law put into math. To utilize this very quickly, we're going to add 10 joules of thermal energy to two separate objects. The first one is at freezing point, the second one is at boiling point. Before even doing any math, which object gains more entropy from this action? Okay. Well, let's prove that now. Let's place all the markers. So, Q divided by, delta Q divided by temperature. We're adding 10 joules to both objects. The 0 degree Celsius object, how many Kelvin would that be? Very good, 273 Kelvin. And then, what is the 100 degree Celsius object in Kelvin? There you go, just add 100. To go from Celsius to Kelvin, you just add 273. So 0 plus 273 is 273. 100 plus 273 is 373. So, which object becomes more chaotic from this tiny amount of energy being added to it? It's the same numerator both times. And in general, a smaller denominator means a bigger number. So, freezing object gains 0.037 entropy units. The boiling object gains whoops, that should be, that kind of defeats the whole exercise, doesn't it? 0.027 entropy units. So it's not a lot. It's not a lot of energy being added to either of them, but the frozen object was more organized. So it has a more measured effect from the same amount of energy being added to it. So, the same amount of thermal energy can create different amounts of entropy depending on what object possesses it, but again, in general, total entropy for the entire universe is always rising. And the third law of thermodynamics. Since entropy is just chaos and disorder, you can reduce that chaos for single objects. You can remove thermal energy from one object, making it colder, making it more organized. That will drive the entropy of that object down. When you increase temperature,